Hello everybody! In this video lecture, we will discuss one-dimensional motion with constant acceleration, freely falling objects, and derivation of kinematics equations. There are three main ways to derive the kinematics equations for constant acceleration. First one is using the graphical representation of motion. As we discussed earlier, the slope of the tangent to the displacement graph gives the instantaneous velocity. Slope of the velocity graph gives the acceleration, and slope of acceleration here is 0 because we focus on constant acceleration. Let's take a look at areas under the motion curves. Area under the acceleration curve all the way to the time axis is a times delta t, and that's equal to the change in velocity. Rearranging delta v, we can derive our first equation, v equals v naught plus at. Now look at the area under the velocity curve. This is final velocity, and considering the equation of the line, y equal to mx plus b, this part is at, and here is v naught. Area of the rectangle is v naught t, plus area of the triangle is 1/2 at times t, gives us the change in displacement. Rearranging this gives us the displacement equation as we know it. We can also derive the kinematics equations using definitions of acceleration and velocity with algebra. Acceleration is defined as the rate of change in velocity, so here is our first equation. Average velocity for motion with constant acceleration can be found by averaging original and final velocities, because it is the midpoint of a linear growth. Clearly, we cannot use this expression if velocity is not linear or acceleration is not constant. By definition of average velocity, we know that change in displacement is equal to average velocity times time. Plugging in the average velocity from before, we have our second equation derived. I'd like to remind you this is valid for constant acceleration only. Now take our second equation, plug in the first equation instead of v, simplify, and here is our third equation derived. And finally, start with our second equation, rearrange v equals v naught plus at to solve for time, plug in for time, a little algebra, and rearrange. Ta-da! Here is the timeless equation. Here is the list of 5 equations you can use to solve all constant acceleration kinematics questions. Please keep a list of equations and make it accessible all the time throughout your study of physics. Let's solve an example problem together. A car traveling at constant speed of 45 meters per second passes a trooper hidden behind a billboard. Let's start recording our givens. So, velocity of the car is 45 meters per second. 1 second after the speeding car passes the billboard, the trooper sets out from the billboard to catch it, accelerating at a constant rate of 3 meters per second squared. So acceleration of the trooper is 3 meters per second squared. How long does it take her to overtake the car? So, how long is the time for the trooper? Is our question. I suggest you start your thinking at the moment of overtake. Which is faster? The car, the trooper, or do they have the same velocity? Well, they are at the same position in time, but Trooper must be much faster because she needs to make up for the times her velocity was less than the car's. Also, if Trooper has a time t, let's say the Trooper has a time t, if the Trooper has a time t, the time for the car is 1 second more than that. Time for the car is t plus 1. So we will use this information to set their displacement from the billboard equal to each other. So displacement for Trooper is equal to the displacement of the car. Now the Trooper has a constant acceleration, so we need to use an appropriate equation for it. So it is v naught t plus 1/2 a t squared. And the car is moving at constant speed, so v car times the time, but its time is going to be t plus 1. There you go. Now, if we solve this equation for the time, which is the time of the Trooper, we are going to solve everything about this problem. Let's go ahead and plug in the values that we know. So original velocity of the Trooper is nothing, starts from rest. So 3/2 t squared is equal to 45 t plus 45. Multiplying both sides with 2/3 gives us t squared minus 30. T minus 30 equals 0. Now we need to solve this quadratic equation. Depends on how you like to solve it. Let's remember the quadratic equation. Negative b plus minus b squared minus 4ac over 2a 30 plus minus 900 plus 120 over 2. Okay, square root of 120, checking, is 31.9. So 30 plus minus 31.94 over 2. Well, the minus is not going to give us a real answer. Therefore, t must be 30.9 something, so it's going to round up to 31 seconds. Well, it takes 31 seconds for the Trooper to overtake. Here is a practice problem for you. Please pause the video, solve using the guess method, and check your answer and work. So I hope you paused. Here is how the guess method works. You have your list of given and unknowns. You just write kinematics equations, plug in your values, and express your answer with units and box your final answer. And here is part B. And now, free fall. A freely falling object is any object moving freely under the influence of gravity alone, regardless of its initial motion, just like this pumpkin falling from the crane. Let's begin with a quick example. Given ball's initial velocity is 25 meters per second upward and acceleration due to gravity is about 10 meters per second squared downward, since acceleration is opposite to the direction of initial motion, velocity of the ball would decrease by 10 meters per second every second. As you can see here, even though velocity continually decreases, speed decreases at first and then increases on the way down. Let's take a look at the graphs of the ball going up and down. It moves in the upward or positive direction with decreasing velocity as shown by the decreasing positive slope of displacement. It comes to a momentary stop at t1, then turns around and speed up as shown by the increasing negative slope of the displacement curve. This means velocity is positive and decreasing until t1, negative and decreasing all the way to t2. I want you to take a moment here, think and reflect the meaning of negative velocity and what is happening to speed and displacement. We measured the magnitude of freefall acceleration as 9.8 meters per second squared. So freefall is just a special case of constant accelerated motion where we know the direction and magnitude of the acceleration. So we could modify the kinematics equations for freefall. Since motion is happening on vertical axis, we could replace all x variables with y's. If we take upward direction as positive, all the acceleration y variables become negative g. So here is our new set of equations just for freefall. There are very useful turning points in freefall motion, such as t1, where object is at the top of its path and velocity is 0. We can find time t1 using the first equation. And t2 is just double t1, or look at it as displacement y minus y naught is equal to 0 and solve the second equation. And finally, maximum height y minus y naught, where velocity y is temporarily 0, can be found using the third equation. Time for another example problem. A stone is thrown from the top of a building with a speed of 20 meters per second. The building is 50 meters high. We need to find the speed it hits the ground with and how long the whole thing took. Alright, the best way to start is to have a list of given and unknown. If we consider the bottom of the building as origin, we can see that our object already has a position y naught, which is 50 meters high. At the end of the motion, our position is going to be 0 meter. The original velocity at point A, v naught, is equal to 20 meters per second, considering the upward direction as positive. And if that's the case, acceleration is negative g because it's pointing downward. Therefore, acceleration is negative 9.8. Alright, now what is the unknown? We need to find what is the velocity just before it hits the ground at point E. Now, sometimes students think about a question like this, the long way, or the wrong way in my opinion, because they think, well, first they have to solve point B, where object reaches to the maximum height, or maybe even they need to solve for point C as well. How long does it take for it to reach the same velocity or same speed as point A? And then they think they can solve for the point E. There is no such thing. If you know the variables at one point, in this case A, we know the original conditions of position and velocity at point A, we can find any other variable at any other point, whether it is B, C, D, or E, makes no difference whatsoever. Just use your kinematics equations, consider the initial and final positions or conditions, and just solve for it. So all we need to solve for what is the velocity at point E. Given the variables, I think the best way to approach this is to use the timeless expression. For example, v at c squared is equal to v naught squared minus 2g y minus y naught. Okay, there you have it. Now consider this. We know the v original, we know acceleration, we know y and y naught. So there is no reason why we cannot find the velocity at point C directly. Alright, so there is no need to rearrange anything, just plug in the variables. So 20 squared minus 2 times 9.8. Now, I hear a lot of students asking me, is G positive or is G negative? Well, G is always 9.8. It doesn't change. What changes is your assumption of what direction you want to call positive, right? G is always positive 9.8. But if your acceleration pointing down, then your acceleration is equal to negative G. So that's the point here. All right, so let's go ahead and plug in everything else. So final y is 0 and original y is 50. All right, so let's solve for this then. Velocity at c is the square root of 400. It's going to be positive now. It's going to be, yeah, positive 980. So solving it with a calculator, we see that velocity at point C is plus or minus, rounding down to 3 significant digits, 37.1 meters per second. Well, which is the answer, plus or minus? They are asking me the velocity, right? My velocity at point E is pointing downward, therefore it should be negative. Well, therefore my final answer, velocity at point C is equal to negative 37 point, that's not 37, 37.1 meters per second. So there you have it. Okay, now let's calculate the total time. Again, we don't need to calculate the time to go A to B and B to E all the way. We can calculate the time it takes directly from A to E. Let's use the velocity equation. Vc is equal to, final velocity is equal to original velocity, what is it? Va or V naught, whatever you want to call it, minus gt. This is the total amount of time in between A and C. Okay, so let's solve for time. Time is equal to VA minus VC over G. Okay, so VA is 20 minus VC is double minus 37.1 divided by 9.8. Okay, checking this from the calculator and rounding it to 3 significant digits, I found this to be equal to 5.83 seconds. All right, so that's the answer. Last topic for today's video is derivation of kinematics equations from calculus. We already discussed about derivative being instantaneous rate of change of a function. Now, let's take a look at the integral. Integral can be considered as antiderivative, just like division is anti-multiplication. Or it is also the area of a region between the curve of a function and the horizontal axis. If the function is a constant, such as y equal to 5, or linear as y equals 2x, finding the area would be very easy. For a curve such as this, we must split the time axis to many small equal intervals and find the sum of all rectangular areas. Smaller we set these rectangles, more accurate the area gets. Please make sure to finish the summer calculus assignment before going any further in this course. Here is a reminder of the power rule. By definition, instantaneous velocity is derivative of displacement x with respect to time t. Rearranging the equation gives dx equal to v dt. Remember, integral is antiderivative. I have the derivative of x and I want to get x. So let's take the antiderivative of the whole equation. It is important to consider the boundaries. At time equal to 0, object was at x0. And at an arbitrary time t, object will be at its final location x, and that's how you determine the boundaries. If v is constant, power rule and the boundaries gives us x minus x0 equal to vt. This is the equation for constant motion. Let's consider the case of constant acceleration. By definition, acceleration is derivative of velocity with respect to time. Rearranging, dv is equal to a dt. To get v, take the antiderivative. At time equal to 0, object's velocity was v0. At time equal to t, velocity will be an arbitrary final value v. A is constant, so v minus v0 equal to at. Now, this is the case for v is not a constant, but v0 plus at. Integrating just like before gives us x minus x0 equal to v0 t plus at squared over 2. Please stop the video here and confirm that this equation checks out. Okay, let's solve an example problem. A car currently moving at 10 meters per second accelerates non-uniformly according to this expression a equal to 3t squared. Find its velocity at 2 seconds. We cannot use any of the kinematics equations here because acceleration is non-uniform. Therefore, we must use the definition of acceleration and calculus. So we know that acceleration is defined as, or instantaneous acceleration is defined as derivative of velocity with respect to time. So if you want to solve for velocity, then we rearrange the equations. dv is equal to a dt and take the integral of both sides. So this starts from original velocity to final velocity, and this integral's limits are from time equal to 0 to all the way to time equal to t. Okay, so the first integral gives us v minus v0, and the second integral, we just have to replace a with its equation. 3t squared 0 to t dt, and v minus v0 is equal to t cubed over 3, so we have t cubed, and from the limits of 0 to t, it's just going to be t cubed. Okay, rearranging all this means final velocity is equal to original velocity plus t cubed, and original velocity is 10 and time is 2 seconds cubed, and final velocity will be equal to 18 meters per second. There you have it. Here's a practice problem for you. Please stop the video and work on the problem. I hope you stopped the video, and here is the answer. Here is another practice problem. Please stop the video just like before and work on your answer. And here is the solution. That's all for today. Don't forget to note your questions for our next meeting. Thank you for listening.